Hi, it's Olivia Becker. I will be teaching you guys about the Doppler effect today. Okay, to begin, I'll give you the drawn out definition for the Doppler effect. And it is pretty much means is the effect produced by a moving source of waves in which there is an apparent upward shift in frequency for observers towards whom the source is approaching, and an apparent downward shift in frequency for observers from whom the source is receding. And I will give you guys some time to jot this down. Okay, next I'm going to give you guys an easier definition that will probably make more sense to everyone. And the Doppler effect pretty much describes the shift in the frequency of a wave sound when the wave source or the wave receiver is moving. And I'll give you guys time to jot that down also. Okay, now I'm going to describe the three common types of waves that use the Doppler effect. And these are the water wave, the sound wave, and the light wave. And the Doppler effect mostly applies to and is applied mostly for physics with the sound wave. So we'll talk about that more next. Okay, these are two tips that will help you understand the Doppler effect better. The Doppler effect actually has no change in frequency, even though that is commonly what is thought. It's just a change in distance from the source frequency. And I'll explain that next with a picture. Okay, this is a picture that I thought could help explain the Doppler effect. So pretty much this is a cop car, and this is the source of the sound frequency or the sound waves. And the closer you are to the source, so distance wise, the smaller the wavelength but the higher the frequency. But if the cop car got closer to this person, then it would become a small wavelength over here and a high frequency. But the farther you are away from the source, the larger the wavelength and the lower the frequency. So just depending on how far the cop car travels determines the size of the wavelength and how high or low the frequency is. Okay, so this is the overall equation used for the Doppler effect that I will explain, and it is F naught equals V plus or minus V naught over V plus or minus Vs times Fs. And FO is the frequency observed by stationary. Fs is the frequency observed by moving object. V is speed of sound, V naught is speed of observer, and Vs is speed of source. And I will explain the equations farther and how they break down and can be used. Okay, this looks pretty overwhelming, but it's pretty much just the equation I gave you right before this, broken down depending on the position of the observer or the source. So if there is a stationary observer and a stationary source, the frequency of the observer equals the frequency of the force. If the source is moving towards the observer and there's a stationary observer, the frequency of the observer equals the frequency of the source times V over V minus Vs. If there's a stationary observer and the source is moving away from the observer, frequency of the observer equals frequency of the source times V over V plus Vs. Okay, move on to the next row. If there's a stationary source and the observer is moving toward the source, then the frequency of the observer equals frequency of the source times V plus V of the observer over V. If the observer is moving towards the source is moving towards the observer, then the frequency of the observer equals frequency of the source times V plus VO over V minus Vs. If the observer is moving towards the source and the source is moving away from the observer, then the frequency of the observer equals frequency of the source times V plus VO over V plus Vs. Okay, last column. If the observer is moving away from the source and there's a stationary source, then frequency of the observer equals frequency of the source times V minus VO over V. If the observer is moving away from the source and the source is moving towards the observer, then the frequency of the observer equals frequency of the source, V minus VO over V plus Vs. And lastly, the observer is moving away from the source and the source is moving away from the observer, then frequency of the observer equals frequency of the source times V minus VO over V plus Vs. So this table is pretty important and will help you solve any problem with sound waves and the Doppler effect. And it is pretty helpful, so please jot this down. I'll give you time to do that. Hopefully that's enough time. Otherwise, I can pause the video. Okay, here's a good example that uses multiple equations from the table, so let's begin. Okay, suppose a train has this 173 hertz horn and is moving at 55 meters per second in still air on a day when the speed of sound is 340 meters per second. Okay, first we're going to find what frequencies are observed by a stationary person at the side of the tracks as the train approaches and after it passes. Okay, so to begin, we got to figure out which equation we need to use. So we are going to have a stationary person, so we can look at our table and figure out if we're in that column. And then we're going to find it as the train approaches and after it passes. So we're going to have to use two separate ones. And then to look at our example, the Fs equals 173 hertz, the V equals 340 meters per second because that's the speed of sound, and Fs is 55 meters per second because that's the speed of the horn. So for the train approaching, we're going to use frequency of the observer will equal frequency of the stationary object times V over V minus Vs. And then after it passes, we will use VO equals Vs, V over V plus Vs. So looking at a table that I just give you, this makes sense based on the question. So next we will figure out the question. Okay, so I plugged in the numbers into the equation and I will give you guys a couple seconds to plug it into your calculators. Hopefully that is enough time. For the top one, I got 206.39 Hz. And for the bottom one, I got 148.91 Hz. Okay, and based off the picture, that should make sense because as the train gets closer, the frequency increases, and then as it passes and gets farther away, it decreases. Okay, so this is the next example. So suppose you're walking westward on the sidewalk at 2 meters per second, and you can faintly hear a 400 hertz ambulance approaching from the east at 72 meters per second, and the speed of sound is 340 meters per second. What is the frequency as the ambulance approaches and as it passes by? So first we're going to decide what is what. So F of S would be 400 hertz because that's the frequency of the ambulance. VO of the observer would be 5 meters per second because that is the person walking on the sidewalk. And then V is 340 meters per second, and that is the speed of sound, the velocity. And then the velocity of the source would be 72 meters per second because that's how fast the ambulance is approaching. So next we will decide what equations we should use for this. Okay, so based on the example I just gave you, we're going to decide the equations. So for the ambulance approaching, you will have to use the frequency of the observer will equal the frequency of the source, the velocity plus the velocity of the observer over the velocity minus the velocity of the source. Because this is based on the ambulance right here and the person walking westward, the ambulance moving eastward, so the source is moving towards the observer and the observer is moving towards the source. And for the ambulance leaving, it will be the frequency of the observer equals the frequency of the source. That's V minus V of the observer over V plus Vs. And this is because the ambulance would be moving past the person, so it'd be moving away from the observer, and the observer would be moving this way, so the observer would be moving away from the source. Next, we will plug in the numbers and solve. Okay, so now we plugged in our numbers into the equations. For the ambulance approaching, the frequency of the observer was 510.45 hertz. And then the frequency of the observer while the ambulance is leaving is 328.16 hertz. Which makes sense again, like I said before, because as the ambulance approaches, the observer and the source get closer, which means the frequency increases. And as the ambulance leaves, the source and the observer get farther away, which makes for a lower frequency. Okay, so that's all I have for the Doppler effect today. Hopefully the examples helped. I tried to do ones where the observer was stationary and then one where the observer and the source were moving. And I hope you can understand the Doppler effect and can continue to use it throughout physics.